So should we start?
Yes.
Okay, very good. So hello everyone, and welcome to the European Non-Associative Algebra seminar. It's a great pleasure to introduce Yuly Billig. He doesn't need an introduction. He's a well-known expert on Lie theory and representation theory, vertex operator algebras, and so forth. And sorry, I forgot to mention his institution, Carleton University in Canada. And he's going to talk to us about Quasi-Poisson superalgebras. So, Yuly, you have the floor.
Thank you very much, Samuel. So first of all, I wanted to thank you, Jabir, and Ivan for the invitation to speak here. So you have a wonderful, active online seminar. So that's awesome. So let me share my screen. So yeah, can you see it now?
I think we can see it, yes.
Okay, very good. So I will talk about quasi-Poisson algebras. So these are exotic objects, but of course, so there is a good reason to look at them. So I'm interested in Lie theory, and so that appeared naturally. All right, so let's start. So if we talk about Lie algebras, then the most important finite-dimensional Lie algebra is, of course, SL2. Oops. Sorry. Right. And if we talk about infinite-dimensional Lie algebras, then the most important infinite-dimensional algebra is the Virasoro algebra. And so here is a well-known Lie bracket in Virasoro algebra. So Virasoro algebra has generators or basis vectors Ln's indexed by integers, and also it has one central element Z. And so this is the Lie bracket in this algebra. And so this algebra is the central extension of the Lie algebra of polynomial vector fields on a circle. And it's a central extension of what is known as the Witt algebra. So we take the algebra of Laurent polynomials and take derivations of it, right? So if we think about a circle and a function on a circle can be expanded in a Fourier series. And then if we are in algebraic setup, then we talk about Fourier polynomials. And if we take t to be e to the ix, so then the algebra of Fourier polynomials is the algebra of Laurent polynomials. And then the derivations of the algebra of Laurent polynomials it should be thought of as polynomial vector fields on a circle. And so if we set Ln to be minus t to the n plus 1 ddt, so this vector field on a circle, then the Lie bracket between Ln's, these vector fields will be as above. And the only thing that's missing is the central extension. And it's well known that this central extension is the unique non-trivial central extension of the Witt algebra. Now, Witt algebra is Virasoro algebra is extremely important, so both in mathematics and physics, and it drives the whole representation theory of infinite-dimensional Lie algebras. And in 1985, Balinskii and Novikov proposed an approach to generalize the Virasoro algebra. And the idea was the following. So let's take some finite-dimensional algebra. So we are not going to specify yet what type of algebra is this. So just vector space with multiplication. And we take the loop algebra of A. So that is, we take the tensor product of A with Laurent polynomials. So this can be viewed as A-valued functions on a circle. And so for simplicity, let's denote the tensor product T to the n times A as just an, and let us consider a bracket that looks a bit like the bracket from the Witt algebra. So the bracket of an with bm is n times a times b, and then we take tensor with t to the n plus m, and minus b times a, again tensor t to the n plus m. And now we ask a question. So what are the conditions on algebra A that will ensure that the above bracket is a Lie bracket? So we want to construct Lie algebra from an algebra A. And so that's a fairly easy exercise. And so the result is that this loop algebra of A is a Lie algebra, if and only if A is what became known as a Novikov algebra. And here are the axioms of a Novikov algebra. So A times B times C is the same as A times C times B. So this means that right multiplications commute. And here is a second axiom. And so if we impose these two axioms on an algebra A, then L of A will become a Lie algebra. And so here we want to point out that the Novikov algebra is some sort of a hybrid of commutative algebra and the Lie algebra. So right multiplications from the first axioms, we see that they commute, so they generate a commutative algebra. And from the second axiom, it's possible to see that left multiplications form a Lie algebra. And so let us give an example. So how can we construct Novikov algebras? So we can, for example, start with the commutative associative algebra and pick a derivation of it and fix a scalar. And then we define the product, new product on A as A times derivation applied to B plus alpha times the commutative product A times B. So here we get the family of algebras parameterized by alpha. And then it's an easy exercise to verify that this will become an Novikov algebra here. All right. And so now what's the idea of Balinskii and Novikov, right? So we want to generalize Witt algebra, and so that we can get interesting generalizations of Virasoro. And of course, Witt algebra is simple. And if we want to get something interesting here, so what we need to do is we need to take a simple finite-dimensional Novikov algebra. And then if we take a simple finite-dimensional Novikov algebra, then this loop algebra L of A will certainly become an interesting infinite-dimensional Lie algebra that's worthy of our investigation. All right. Unfortunately, so their plan failed. So when in 1985, Novikov was giving a talk on this brand new Novikov algebras, Yefim Zelmanov was in the audience, and so immediately after the talk, Zelmanov told Sergei Novikov that he can prove that every simple finite-dimensional Novikov algebra is one-dimensional. Obviously, Sergei Petrovich Novikov was a bit irritated by this, and it was shocking to him. But Zelmanov indeed gave on the spot, so gave a proof that every simple finite-dimensional Novikov algebra is one-dimensional. And this one-dimensional Novikov algebra corresponds to the Witt algebra that we started with. And if we go to the super case, so if we consider Novikov superalgebra, so then there is one more simple Novikov superalgebra. It's two-dimensional. And the corresponding L of A is also very important. So this is known as Ramon superalgebra. So these give important examples, but unfortunately, we did not get anything new that we wanted to get. All right. So now, at the same time, so there is a class of simple Lie superalgebras that physicists care about a lot. So these are called superconformal Lie algebras. So they appear in string theory, and physicists like this Lie algebra, and mathematicians as well. All right. So what is a superconformal Lie algebra? So an untwisted superconformal Lie algebra is a Lie superalgebra with the following properties. So first of all, it contains a Witt algebra as a subalgebra. And then it has a Z grading. And this Z grading is induced by the Carleton element of the Witt algebra. So basically, it acts in a joint action. Its eigenvalues are integers, and this defines the grading on L. And the last axiom is that we require that these dimensions are uniformly bounded. And so then we can apply a representation theory of the Witt algebra to study these objects. Of course, for applications, not just these algebras, but their central extensions are important. But now this is kind of a second stage, a fairly routine stage, that first we define the superconformal algebra without the central extension, and then we look at central extensions of these algebras, and many of them have interesting central extensions. All right. And so just a few years after the work of Balinskii and Novikov, Kac and Leur gave a conjectural list of simple superconformal algebras. So this Kac-Leur conjecture about this classification of superconformal algebra is still open. So we don't have a proof that this list is complete. Now, all the algebras on the list of Kac and Leur are subalgebras in this algebra. So we take super vector fields. So we take Laurent polynomials and tensor Laurent polynomials with the Grassmann algebra, right? And so we get a Lie superalgebra of super vector fields, right? And the Z grading here is given by Laurent polynomials. So the powers of T will induce the Z grading on this algebra. And so what is the list of Kac and Leur? So, well, first of all, we have this Witt algebra W1n itself. So it's a simple superconformal algebra. So it has a Witt algebra as a subalgebra, and it has a Z grading. And one can check that all components of Z grading have the same finite dimension. So this goes back to like old Carleton classification, but now applied to superalgebras. So then we have the Lie superalgebras of divergence 0. So here it is possible to define divergence 0 vector fields. Okay, when we talk about divergent zero vector field. So this is divergence zero is measured with respect to a volume form, and there is some flexibility how one can how one can choose the volume form here. And because of that, so we get a family of algebras. So they're parameterized by n and also by the scalar alpha here. And to get the simple algebra, so these algebras are not always simple, so sometimes we need to take the derived subalgebra of that. And also there is, when n is even, there is a different choice of the volume form, and there is another family of divergence zero superalgebras. So again, this will be subalgebras in W1 to n. All right, so then there are contact type superalgebras, so Kn, right? So these are simple when n is different from 4, and when n is equal to 4, then we need to take the derived algebra, and so then we get simple algebras. And so this was the list as it was presented in 1989, and so there was a surprise that about in the next decade, in 1997, there was another superalgebra, simple superconformal Lie algebra, was discovered by Cheng-Kac and independently by Shepechkina. So this Cheng-Kac algebra CK6 it was added to this list. But again, this is still conjectural. So this means that we need to still work on proving that this list is complete. Now, so this is something that looks like what Balinskii and Novikov wanted to do, right? So we want to generalize Witt algebra, and so these are interesting and important super generalizations of the Witt algebra. So yet, so these conformal superalgebras, so they cannot be described using Balinskii and Novikov construction. So the construction of Balinskii and Novikov is not flexible enough to cover these algebras. However, it's very close, and so we only need a very minor modification to the construction of Balinskii and Novikov in order to cover the algebras from Katz-van der Leur classification. And so what we do is the following. So now let us consider an algebra with two binary operations, right? So we take A and we assume that A is like a product, then it has a bracket, and it also has a unary operation that I will denote by P, right? So we have an algebra with two binary and one unary operation. And we take a loop algebra of this. So this means that we take a vector space, which is a tensor product of Laurent polynomials with this algebra A. And we define the bracket in the following way. So we take n times A times P of B, right? So minus M times then B times P of A, right? So these expressions look like a little bit like examples from of a construction of a Novikov algebra. But then we add one more term. So we add the bracket of AB, right? And all of that is multiplied by T to the M plus N, right? So we take this construction, and then we ask, so under what axioms on this algebra we will get a Lie algebra, right? So basically, so this is a fancier generalization of the idea of Balinskii and Novikov. Right? And so basically, the new thing here is the last term, essentially, right? So the so in Balinskii-Novikov, there was no, so to speak, constant term in the above bracket, and so here we put one. And so then this leads to the definition of a quasi-Poisson algebra, right? So what we have is an algebra with two binary operations, the product and the bracket, and one unary operation. So it's called the quasi-Poisson algebra if, so with respect to first product, it's a commutative associative unital algebra. With respect to the bracket, it's a Lie algebra, right? So basically we have an algebra with commutative product and a Lie bracket, right? So this already sounds a little bit like Poisson algebra, so because this is exactly what we have in Poisson algebra. And we have an axiom on operator P, or on this unary operation. So basically what this axiom says is that P is very close to being a derivation of the commutative algebra, of the commutative product. So basically P is identity operator plus a derivation, or P minus identity is a derivation. So basically, so choosing P is equivalent to choosing a derivation of the commutative algebra. But there is one more axiom. And so here is one more axiom that ties together all three operations, right? So here we have the Lie bracket. Here we have commutative products, and here we have the unary operation P. So this is the definition of a quasi-Poisson algebra. And so of course, it's straightforward to make a super version of this definition, right? So like it's standard technology, right? So if we can define for something for ordinary case, then so it's immediately we know how to write down the axioms of quasi-Poisson superalgebras. And I decided not to do this, simply just, not to have all these negative signs thrown around. So just for clarity of exposition. But so when we say that we define quasi-Poisson algebras, so we also understand that we also define quasi-Poisson superalgebras. And here is a theorem that if we have a quasi-Poisson superalgebra, then its loop algebra is a Lie superalgebra with the construction that is given above, right? So if we go back, right? So this if we start with a quasi-Poisson superalgebra, so then this bracket, of course, with the appropriate negative signs in the super case. So this will be a Lie superalgebra. All right. And so let us point out what happens in this Lie superalgebra. So element one, right? So we said that A is supposed to be unital commutative algebra. So then the unit of A will generate the Witt subalgebra. So again, so that's easy to see from the Lie bracket. And so then one can also check that we will get a superconformal algebra if and only if, so you see, we have this commutative unit, but we also have the Lie bracket, right? And so what we can do is we can consider the adjoint operator of this commutative unit, right? And so we require that this adjoint operator of 1 is diagonalizable on A. And so if it is, then this loop algebra will become a superconformal algebra. So then we will get a Z grading on L of A given by the eigenvalues of L0, right? So this L0 is essentially the element 1 tensor t to the power 0, right? So, okay, so now let us give some examples. So how easy it is to construct quasi-Poisson algebras. So, all right, so for example, we can start with the Poisson algebra. So let's take a Poisson algebra. So this means that we have a commutative product on A and a Lie bracket, and a Lie bracket is a derivation of the commutative product, right? So this is what the Poisson algebra is. And then let's choose one more derivation of the commutative structure such that, so if we add identity to it, then this new operator P will become a derivation of the Lie structure on the Poisson algebra. And then if we can do this, then we will obtain a quasi-Poisson algebra, or QP algebra for short. Right? So if we have a Poisson algebra with the special derivation, which is a derivation of the commutative structure, and if we add identity, then we will get derivation of a Lie structure. So then this will be a quasi-Poisson algebra. So then another example is the following. So again, let's start with the commutative associative unit algebra with a derivation. And then set a new Lie bracket as, so a similar formula that, well, something similar to this idea that we saw in Novikov algebra. So we define a Lie bracket as A d of B minus B d of A. So it's clear that this is a Lie bracket. And then we set P to be a derivation plus identity. And so then A will become a quasi-Poisson algebra. So this means that this gives us an ample array of quasi-Poisson algebras. Right? So because all we need to do is we need a commutative associative unit algebra, and we know a lot of them, and just one derivation. All right. So then another natural example is the following. So let's again take a commutative associative unital algebra, C. And let's take V to be the Lie algebra of derivations of C. And let's put them together. So we define A to be a direct sum of the commutative algebra with its derivations. And what I'm going to do is I'm going to extend the products, right? So we have the commutative product that is defined on C and the Lie bracket that's defined on V. But now I want to extend this. So I want to define the commutative product on the whole space and the Lie bracket also on the whole space. And so this is done in the natural way. So if I have element of A, which I think is a function, times a derivation, so then there is a natural operation. We can just multiply derivation by a function, and this will be a new derivation. So this will be the product of an element of C so this is a commutative product of an element of C with an element of V. If we take a Lie bracket of an element of E with the element of C, so we have a vector field or derivation and the function, then the Lie bracket between them is a function or element of C that's applied. So we just apply a derivation to a function. And so then we get an element of C. So this is how we define the Lie bracket between these two components. And the Lie bracket of two functions is defined as 0. And likewise, the commutative product of two derivations is also defined as 0. Right? So now we have a vector space with two binary operations. So we define the commutative product on this, and we defined a Lie bracket. And finally, we define operator P, which will be identity on the commutative algebra and 0 on derivations. And so then this will give us a Quasi-Poisson algebra. All right. And so now what happens is that now we can look at superconformal Lie algebras from Katz-van der Leur list. And we can see that all of them actually come from Quasi-Poisson algebras. So we can take the Grassmann algebra, and so Grassmann algebra is, of course, is a supercommutative unital algebra, and we can take the derivations of the Grassmann algebra, and now we can just follow the previous construction. So we can take the direct sum of Grassmann algebra with its derivations, and so then if we apply, so this will give us a Quasi-Poisson algebra or Quasi-Poisson superalgebra. To this superalgebra, we can apply the loop construction, and the loop algebra of this will be the full Witt algebra W1n. So this means that from this construction, we can recover this biggest, like the master superalgebra. All right. So next, let's look at the superconformal algebras of contact type. So usually contact type is difficult to describe. So if we talk about contact Lie superalgebras, so then the definition is not very easy to work with. So however here, so if we want to do it through Quasi-Poisson algebras, then this becomes fairly simple. So what we do is, again, let's take the Grassmann algebra and let's define the Poisson bracket here. And so this Poisson bracket is, so the formula is somewhat similar to the Poisson bracket on the space of polynomials, except we are in super case, so it's not quite commutative, right? And so here, what I find is that it's convenient to work not with, so it's convenient to distinguish left derivations from right derivations. And so here it's convenient to use right derivations on the Grassmann algebra. So basically, what's the idea of a left derivation? So suppose the usual, so we want to take derivative with respect to, say, psi I, right? So how the left derivation acts? So the left derivation is the following. So if, say, a monomial does not contain psi I, then this derivation is equal to 0. But if it contains xi, so what we do is we will want to pull xi factor to the left, right? And so this will, when we do this, we will incur some signs. And then when it's on the left, we can differentiate by it and just erase it, right? So, but then this also can be done from the right. So this means that now the right derivation by xi is, so we pull xi factor if it is present to the right. And once we do it, then we cancel. So then, of course, in super case, so the law of signs for right derivations will be slightly different from the left derivations. But if we use them, then this formula for the Poisson bracket will look in a very simple way. So there is no need to put any negative signs. That's impossible to remember, right? And then we also set P, which is identity plus a certain natural derivation on the Grassmann algebra. And so now what we have is, so we have basically of all of our operations. So we have the commutative product or supercommutative product on the Grassmann algebra. We have the Lie bracket on the Grassmann algebra. And we have this operator P. And so this will be a Quasi-Poisson algebra. And so if we take the loop algebra of that, so then this becomes a conformal Lie superalgebra of contact type. And so for contact type, the Quasi-Poisson algebras are way easier to describe than the contact Lie superalgebras themselves. So there is advantage of extra simplicity, right? So again, this is very typical in Lie and non-associative story, is that the definitions that we give, say like a definition of a Lie algebra, does not seem to be natural at all, right? So when we see it for the first time, but then it turns out that it's a nice object to work with. All right, and so let us finally describe what is a Cheng-Kac's superalgebra. And again, here it's easier to describe this at the level of Quasi-Poisson algebras than for the infinite-dimensional superalgebra itself. So to describe Quasi-Poisson algebra that corresponds to Cheng-Kac's, so we take a Grassmann algebra in 6 variables, right? So this is a finite-dimensional algebra of dimension 2 to the power 6, and it's graded again by powers of our variables. So we have components of degree that changes from 0 to 6. And what we're going to do is we're going to split this Grassmann algebra in 2 halves. So we're going to keep the half of it. But so this Grassmann algebra has a middle component. So lambda 3 is the middle component of this grading. And it needs to be split in 2 pieces. So we want to define a polarization of the middle component. So we want to split the middle component in 2 subspaces. So for this, we define a Hodge dual of a monomial of degree 3. So the Hodge dual of a monomial is another monomial such that their product is the product of all generators in kind of regular order, right? And now, so we have 2 components that are so defined using this polarization. We take monomials plus I times the Hodge dual of this monomial. And then it turns out that this will split the middle component in 2 subspaces, and this lambda 3 is going to be the direct sum of these two subspaces. And then, so here what we take, so to construct a Cheng-Kac Quasi-Poisson algebra, we take the components of the Grassmann algebra 0, 1, and 2, and we take the positive part of this polarization of lambda 3. So this means that, so here, the Grassmann algebra has dimension 64, and this is half of it, so this will have dimension 32. So this is a 32-dimensional space. And on the Grassmann algebra, we have the supercommutative product, and we have the Poisson bracket as described in when we just talked about contact Lie superalgebra. So there is a Lie bracket on there is a Poisson bracket on the Grassmann algebra. And so it turns out that this space that we take is closed under Lie bracket, under Poisson bracket, right? And the thing that we throw away is the ideal in with respect to the commutative algebra structure. So this means that this space is some sort of, we view it as a subalgebra with respect to the Poisson bracket, and as a quotient algebra with respect to commutative bracket. So now this becomes a space with two operations, and the operator P is defined in the same way as before. And so then so here so this becomes we obtain the Quasi-Poisson algebra structure on this space, and the corresponding loop algebra in the Cheng-Kac superconformal algebra. And now, of course, so we come back to the question of Balinskii and Novikov, right? So we would like to classify finite-dimensional simple quasi-Poisson superalgebras. And so the expectation, and we know that now we have, so this classification is going to be non-trivial, because from Katz-van der Leur list, we have already several interesting simple finite-dimensional quasi-Poisson superalgebras, right? It's interesting to see, so again, I don't know the answer to this even in the non-super case. So the only simple quasi-Poisson non-superalgebra that we know is one-dimensional. And so the question is, are there other simple quasi-Poisson non-superalgebras, right? So, but in the super case, we know that we have several interesting simple quasi-Poisson superalgebras. So it is an interesting question to classify them, and this is one of the possible approaches to see if the list of Katz and van der Leur is complete or not, right? So this correspondence, unfortunately, is not perfect, right? So we cannot say that any superconformal Lie algebra comes from a quasi-Poisson algebra. It's only those that we know all come from quasi-Poisson algebras. But again, if we can construct more simple quasi-Poisson algebras, then it's going to add to the list. Well, again, so there is some additional condition, right? So the joint of one should be diagonalizable, right? So in general, it's not clear why this should hold for simple algebras, but again, there are open problems that one can work on here. And so the final part of my talk, I just want to mention representation theory, right? So with Maliheh Yousufzadeh, who visited Carleton last year. So she is from University of Isfahan. So we looked at representation theory of quasi-Poisson algebras, and it is possible to define what is a module for quasi-Poisson algebra, right? So quasi-Poisson algebra has these three operations, right? And so when we talk about modules for quasi-Poisson algebras, then so on this module M, we should have a representation of a commutative algebra. And we will denote this action of the commutative algebra by phi on M. And we should have a representation of a Lie algebra. So A is also a Lie algebra. And so then we should have a Lie algebra action, and this will be a different action of A on M. So we have these two actions. And also we should represent our unary operation with an operator on the module. And so then we impose these axioms. So we rewrite axioms of a quasi-Poisson algebra as axiom for the actions. And so this is one axiom that describes the action of pi. And there is a second axiom that needs to be satisfied. All right. So again, this is written in a non-super case. And in a super case, there are obvious places to insert the negative signs. And if we have such a module, then so if we have a representation of a quasi-Poisson algebra, then by tensoring it with Laurent polynomials, we will get a representation of the corresponding Lie algebra or Lie superalgebra. And again, so this is one of the ideas in infinite dimensional Lie theory. So when we study infinite dimensional theory, so we somehow want to reduce it to a finite dimensional theory. And so this is one of the things that quasi-Poisson algebras achieve, because here, by studying finite dimensional representations of finite dimensional quasi-Poisson superalgebras, we will construct infinite dimensional representations for infinite dimensional conformal superalgebras. Right. So with Maliheh, we have some additional results on representations of certain of the above quasi-Poisson algebras, but they are technical, and so I'll probably not going to present them here. That's all that I wanted to say about quasi-Poisson algebras. Thank you so much. And so if you have any questions, I will be happy to answer. Thank you.
Thank you very much. Thank you very much, Yuly, for such an interesting talk. Are there any questions? I have a quick question. Your definition
please.
Module for the quasi-Poisson algebra, was it so that you would have this kind of a theorem? I mean, those
Yes.
I puzzled by the last relations.
Right. So basically, all right. So there is no mystery here. So that's so if we look at maybe at the axioms of the quasi-Poisson algebra. So yeah. So here. So we'll look at the second axiom, and we see that element C is always on the right. Right. So so now basically we replace it with a vector from a representation, right? And it's clear what we need to put. So basically it's a straightforward translation, and it works, right? So this gives us a way how to guess these axioms. Right. But then, so we verify, and it seems that everything is consistent, that if we just impose these axioms on the module, then we will get a representation of the corresponding loop algebra. So as expected.
Okay, thank you. Are there other questions? Okay. Well, just another quick question then.
Oh, please.
For example, can you maybe a very innocent question? So, I mean, when you do this construction from the Quasi-Poisson algebra representation to the representation of the Lie algebra, then at the level of the Lie algebra you have tensor products. You can do tensor products of representations. Can that be pulled back to some kind of a property on the Quasi-Poisson algebra? It wouldn't
Right.
be.
Right. So yeah, so this is more maybe a question about universal enveloping algebras, right? And so we discussed this with Malihe a little bit, right? So we don't have a perfect answer for this, right? So it is possible to say what's a universal enveloping algebra, but more work needs to be done. So, for example, so the question is, right, so would the universal enveloping algebra of a Quasi-Poisson algebra have Hopf algebra structure? Right. So I don't know. So maybe one needs to consider a special class of representation. So for example, here I wouldn't take just the tensor product of representations, but you see these representations that we construct, they have additional structure that they are modules over Laurent polynomials. And then you can take tensor products over Laurent polynomials, right? So again, so this is something to look at. So it's very good question, Sam. Yeah, thank you.
Thank you. So I don't know if there are no further questions. Maybe we should thank Yuly for the excellent talk. And well, thanks again. And
thank you.
hope see everyone next week. Bye-bye.
All right. Bye, everybody.